Hello, I'd like to welcome everyone to the National Cybersecurity Student Association monthly webinar series. My name is Gustavo Hoelzer, Executive Director for the Student Association. Today's webinar is Exploitation over Time, Stacks, ASLR, DEP, and ROP, and our presenter is David Hoelzer, instructor at SANS. Exploitation over the last 20 years. Exploitation has evolved over the last 20 years. This webcast covers the history of exploitation and the defenses that have been engineered to protect our systems. We will walk away from this webcast clearly understanding the mechanics of most types of exploitation, how the defenses work, and how easily they can be bypassed, all of which provide strong motivation for a close look at your organization's past cycle. Throughout the webcast, David will demonstrate step-by-step walkthroughs of each of the exploitation, building upon the exploit as defenses are added on the target system. Even if you are not super technical, they're really important takeaways. At this time, I would like to pass it over to David.
Thank you very much, and it's a pleasure to meet you all. Good morning or afternoon or evening, just depending where you're tuning in from. As we get started in this presentation, just a little bit about myself. Thank you very much for the introduction, and I'm glad for it because I don't really like to talk about myself very much. But part of the reason we're partnering with NCSA on this is also just to give you a taste of some of the material that is covered inside of the STI Masters of Information Security Engineering and in the management program as well. I've got a little bit more information about that as we get to the end. As we go through this too, I want to tell you that normally I deliver this as a 2-hour keynote. So as you can imagine, we're going to try to get as much of 2 hours into 1 hour, just do the best we can. So I may have to cut short some of the demonstration, and we're likely not going to actually walk through doing ROP because that can be quite intricate. But we will certainly describe how that works and cover as much of it as we can. Also, as I go through it, as was mentioned, there is a fair amount of technical content in this. But please, if you're not a technical person, don't let that dissuade you. Don't let that turn you off. Don't turn off the webcast. Instead, there's something bigger that I want you to look for. I want you to stand back from the exploitation piece, stand back from the idea of, would I be able to do what's being demonstrated? And instead, there's a really important takeaway that you're going to be looking for, and that takeaway has to do with how we can apply this into our own business. It has to do with a question I'm going to ask very, very early on. So let me go right into the material. In placing this evolution of exploitation into a context, let's put it in the context of how organizations go about doing patch remediation, vulnerability remediation in the enterprise. When I talked about mean time to repair, which is what that MTTR is that I have at the top of the slide, the mean time to repair is how long it takes an organization to go from the point of being aware that something's wrong to actually being able to resolve the problem. So in that context, let's imagine that an organization like Microsoft puts out a new alert. They say there's a critical vulnerability, there's a patch that we're making available to you, and they make this announcement on March 13th. Now, I'm actually taking this from real history, so we're not making that up. So they really did announce on March 13th of 2016, hey, there's this new critical vulnerability in RDP. We really urge you to patch this as quickly as you can. Now, if Microsoft is telling you this is really important, you've got to get this out now, organizations do react a little bit more rapidly than otherwise. But even with that, they don't always react. And we've got a great example of that. We'll tie it in with something that just happened this week in just a little while. But why don't organizations react? Why don't we patch things quickly? In most organizations across the industry, we find that the average patch cycle, at least the patch cycle that we say that we follow, is 30 days. And we say that, but in the real world, not many people are actually hitting that. And we find that people are far outside of that 30-day window. Why 30 days? Where does that number come from? Well, most information security standards that talk about patching in some way usually give you a threshold of 30 days for the application of all relevant patches. Why don't we patch? What is the resistance to patching? Does it really take 30 days to patch things? Well, there's work involved. We should be testing patches before we roll them out, and the larger our enterprise is, the more difficult the testing is. And the smaller our enterprise is, the more limited we are on resources and personnel who actually do testing. So there's always some resistance to patching. Part of this resistance can also be from the point of view of administrators who look at the idea that the patch has come out, they see that it's there, they research what it is, and they say to themselves, sure, there's a problem, but I don't think we have any of that. Yet what we find is most organizations really don't know what they have and what they don't have. One of the critical controls that's pushed out by the Center for Internet Security, actually the first two controls, have to do with really identifying what's on your network and what's in your systems. And it's something that we are just horrible at as businesses, which is why it's the first and second control to know what you have. So looking at a patch that's being released and saying, well, I don't think we have any of that, that's not good enough. It can't be that you don't think you have it. You have to know you don't have it. And if you don't know, you should be looking, you should be finding out, and creating a process that informs you what you have and where it is. That's a little outside of our focus here today, though, so we'll leave that alone, but we can see why that happens. The next reason that would be given for not patching is, sure, there's an exploit, or I'm sorry, a vulnerability that's out there, and there's a patch available, but there's no exploits yet. In fact, Microsoft releases a patch. Sometimes they release them out of band meaning not on Patch Tuesday. And yes, I know Microsoft has said there is no more Patch Tuesday, but strangely, we keep getting patches on Tuesday. So whatever the deal is with that, if Microsoft is releasing it out of band or outside of normal patch cycle, they're telling us this is really important. And even if they're saying to us, there's no known exploitation in the wild, in other words, no one knows about this, that's what they're claiming, I'm not sure that's true. Because if no one knows about it, then why are you needing to release this patch out of cycle? Still, there's this feeling on the part of administrators that there's no known exploits out there yet, and after all, even with the patch available, exploiting this would really be hard, wouldn't it? And that's really what we're going to focus on in this presentation. How hard is that really? How critical is that mean time to repair? Well, when we started out with March 13th, by March 15th in this real-world example, there were researchers in academic circles who were saying that we have a working proof of concept. We can show you how this thing works. Now, have you been patched yet? So that's less than 48 hours. There's a working proof of concept. Even so, there still could be some resistance. I mean, it took these smart people 2 days to figure that out, but it's not in the wild so much. By that afternoon, it's now seen in the wild being used to exploit systems across the internet. So we went from there's an issue, knowing there's an issue because there's a patch available, to being exploited in the wild within 2 days, within 48 hours. We said standards generally allow you up to 30 days, which is clearly too much based on that. But how hard is the exploitation? This would be very, very few people who could actually do this, right? That's actually a myth. That's just not true. What we want to take a look at is how hard really is exploitation. And we're doing that in the context of how does exploitation work? What did it look like starting in the 80s and 90s? And what is involved in it today? We'll be taking a look at a particular class of vulnerability because obviously there are many different ways our systems could be compromised. So we'll just look at one and how different protections have been layered on top of that over the years. And the one we've selected is actually the prime kind of vulnerability that we're continuing to try to evolve security protections against. There are other types of vulnerabilities that have largely gone unprotected and unaddressed. They still exist. They can be exploited. Exploiting them is actually no more difficult than what we're going to do, but the theory behind the exploitation is a bit more difficult because it involves memory management and things like that. So we're going to stay away from that. As we work through this example and talk about both the attacks and the defenses, we're going to be looking at this from the point of view of a security researcher. Whether you want a security researcher to be a hacker or a white hat person who's doing research within the organization to see what could be done. That means that we're going to be looking at what the possible issue is, seeing if we can research how to exploit it, and then create a working proof of concept. That's what we're going to try to do. We're going to try to do it all in 60 minutes or less. And trust me, we will get there in 60 minutes. But to do that, we have to lay out a little bit of groundwork here, a little bit of theory. And this part, there is some theory you have to know. You don't have to know it deeply, so just bear with me for a few minutes, and we're going to jump right into the demonstrations. We're going to be taking a look at a very particular class of vulnerability. We're looking at an overflow vulnerability, and in dealing with overflows, we're specifically going to be dealing with a stack overflow vulnerability. Stack overflows represent an extremely common class of issue that we find in code, and also one of the most commonly exploited issues. It's exploited because it's super, super well known, and the exploitation is very straightforward. There are other kinds of exploitation. For example, heap overflow exploitation is also perfectly viable, and with a little bit of training, a little bit of know-how, it is just as easy to attack those. But getting involved in heap exploitation is a little bit more of a hurdle. It involves having to understand how dynamic memory management works and all those memory structures. We don't have the time to go through that now, so we'll stick with stack overflows, and it turns out that the ground is fertile for finding stack overflow issues even today, even with all of the different mitigations that we have in place. When we deal with an overflow, whether it's a stack or a heap, it essentially means that we're going to take too much stuff and try to push it into too small a space. I have some friends who live out in Las Vegas. My wife and I lived out there for a while. Ron and Luce, when they were getting married, Ron, who was a carpenter at the time, made a sort of a set of pigeonholes, if you think about how old printouts used to be handled, sort of like a little locker for her shoes, a little thing to organize her shoes. It was an 8x8 box. So there's 8 little partitions for each row, and there's 8 columns of these things. And his view was that Luce could have as many shoes as she could fit into that rack. And after all, how many people need more than 64 pair of shoes? Now, if you're married, you might know that 64 pair of shoes might not be enough. For most men, more than enough. We usually have maybe 3 or 4 pair of shoes. But for Luce loves shoes. So within the first couple of weeks, she had more than 64 pair of shoes that she needed to put into her shoe caddy. What happens when she gets to pair number 65? Now, you're probably thinking about physical shoes, so she could cram them in there, but you know, she loves her shoes. She's not going to cram shoes in. She's going to place them carefully. So they're not going to fit. It's going to overflow. You're going to have shoes on the floor. And that's exactly what's happening in an overflow condition in a computer. Because within the memory of the computer, you could think about each of the bytes representing one of those boxes. It's true that we do have bits, but generally speaking, we do not deal with anything smaller than a byte as a discrete memory unit inside of a computer. And as you deal with different architectures, how many bytes at a time you address can vary as well. That's a little outside of our discussion too, but it might come into play with some of our exploitation. We'll see what happens. That means that in the memory, which is just organized logically and in a linear fashion, if I have a certain amount of space allocated to be used for a particular function, and then I try to put too much stuff in it, I'm going to end up overwriting other content, just like Luce's shoes flowing out of the box. In overwriting the other content, what could get overwritten? Well, we have on the screen here a diagram that illustrates the general layout of a computer program within memory. Within the memory, when you start running a process, processes are allocated memory space, and these days, in fact, each process usually has it's as though it's the only process on the machine. Each one has its own paged memory, its own virtual memory allocation, usually given the full 4 GB space, and it's usually allocated in this way. At the very bottom, we have the text segment, which actually doesn't contain text. The name is just for historical purposes. That's the actual code. That's the program. Above that, we have statically allocated global variables. Above that, we have a thing called the base started by symbol, or BSS. These are also global storage, but uninitialized, things that don't have values. After that, we have the heap. The heap is used for dynamic memory allocation. So as we need to allocate more, or release things back, that's managed dynamic memory. Above that, we have a thing called the wilderness, which sounds like a dark and dangerous place that we're going to try to stay out of as much as we can. And then above that, we have the stack. Now, the stack sits at the very top of the memory, and that's what we're going to be focused on. As you can see on the left, we've just put a little call out there. The stack is used for local variables within functions and program flow control. So as we call functions, the stack is going to be used to keep track of where we were in the program so we can return execution there later. The heap grows upward and the stack grows downward. Now the stack is exactly what it sounds like. Saying that it grows downward can be confusing, so forget that for just a moment, and instead imagine that you've gotten a job at a restaurant working as a dishwasher. As you stand in front of the sink, there's a pile of dishes sitting to your right. Which dish will you wash first? You're not going to go for the bottom dish, not unless you're a really stubborn and difficult person. Instead, you're going to reach over and take the top dish off that stack of dishes. And then you're going to wash the next dish, and then the next dish. And when a waiter or a busboy comes in and he puts more dishes down, he puts them back on the top of the stack. He does not lift the dishes up, put the new dishes down, and then put the old dishes on top. Instead, he puts them on the top of the stack. This has a very specific name when we deal with data structures and memory within computer science. We call it a last in, first out queue, or a stack, as opposed to a first in, first out. That would be a queue. That would be standing in line. So if more people come on the line later, they go at the back of the line. Not so with a stack. Whatever's added gets added to the top of the stack. In our illustration, coming back to the slide though, we said that the stack is sitting at the top of the process memory. This represents a problem because if the stack were to grow up, the stack would be growing out of the process memory. It can't do that. So instead, you need to imagine your stack of dishes and imagine that gravity has been reversed and that the dishes are now coming down out of the ceiling towards you. The top of the stack is actually the closest dish to you, the one that from your perspective is on the bottom. So the top of the stack, looking at this diagram, is always going to be at the lowest memory address. The stack grows down into the wilderness and the heap grows up into the wilderness. Of course, it would be a terrible thing if the stack and the heap ever hit each other, so that's a very special condition. It should not ever happen. We're not going to worry about that either. But knowing that this stack is used for local variables and program flow control, and that the stack grows downward, turns out to be extremely important. When we're talking about how this stack works, knowing that it's used for passing arguments, or can be used for passing arguments as programs execute, as they call functions, and that they're used for all local variables within functions, which will often be buffers and other kinds of things, and that it's also used to keep track of program flow. If you imagine you're reading a book, imagine you're reading a college textbook. You get to a word within that college textbook that's unfamiliar. Most college textbooks will have a glossary in the back. So what might you do? Could you imagine taking your hand and putting your hand in that page, turning to the back to look the word up in the glossary, and then you just use your original hand to flip the book back. You used your hand like a bookmark. The stack is used in very much the same way for program flow control. A program is executing, and then it gets to a point where it tells the program to go and execute some other code. So it needs to have a bookmark. It needs to put a finger in the page. It uses the stack for that, to keep track of where the program was. And we can show this to you in pictures. Let's give you an example of a really bad piece of code that's horribly flawed. Don't worry, this is not the code we're going to exploit. We're just going to use this to illustrate how the stack works. You do not have to be a programmer for this either. So if you start instead at the bottom, and I'm sort of hoping you can see my mouse. I actually can't see what you're seeing, so I'm hoping you see my mouse there. We're looking down at this main function. By convention, that's where this program begins executing. And within this function, it's defining some global variables here. We've got a character array called A that's going to contain capital C, capital A in it. That's going to be something that's sitting down at the very bottom, just above the code. If you remember back to our diagram, let me flip back there for a second, that would sit down here in this data piece. because that's something that's both globally allocated and already defined. And then we have this printf function that's getting called, and that is making reference to another function called getInput. GetInput is a function that we've defined. When this function gets called, the stack will be used to keep track of where we were. This function can execute. It will allocate some memory and then call another function. Let's actually watch what might happen on the stack as this happens. I've put on the screen a picture of a stack, and I've put some addresses on the left-hand side there. And if you notice on the left-hand side, the lower addresses are sitting at the bottom. And sorry, this one here, apparently I just didn't change the size. Let me just fix that one because it's going to bother me. Kind of escape the edit there. So the addresses at the bottom are smaller, and the addresses at the top are bigger, which makes sense. That's memory, right? So we're going from lowest to highest. It means, though, that as the stack grows, as we add things to it, the things are going to be added into these gray boxes down here at these other memory locations. I have arbitrarily decided, I have said that this variable, this char A, is being allocated at BFFFFF4, so that's just where it is. If I move down just a little bit, so if we take a look at our next piece of code here, we've got another variable C. Now some other things have happened here. As the program is executing, let me go back for 1 second. As the program is executing, we've got the capital C, the capital A sitting in here. Program executes and we make a call to that function. Other stuff got added in here. What's being added into the stack now are where we were, so where the program code is that we're going to go back to after this function finishes executing. And then this next thing that I've put in green, you might notice, now the numbers are backwards here, but let's read it from the right to the left. BF, FF, FF, F0. Well, if you look, that's this value right here. What happens is that in a function prologue, when it begins running, typically what happens is that the call will put the current instruction pointer on the stack, and then the very next thing that will happen is that the current stack pointer value will be pushed on the stack as well. After that, there is local allocation, so the stack pointer will be moved down, and so here ESP is now pointing way down here, and we've got the allocation for local variables. The reason that this value is pushed on the stack, and it's also stored somewhere else, is so that when this program finishes executing this function, it can clean the stack up. It can put everything back where it was and then resume execution of the other function. Now, some of that is a little bit more technical detail than we need. So let me move ahead. Let's say that at this point, we've got this other buffer here called C. So going back to our code, that's this variable right here, this array, 16 bytes is what we've got for it. And we've put in the word hello. So we end up with HELLO with a bunch of nulls, with zeros. No problem. And this function or this code will execute cleanly as is. What happens, though, if we put more than 16 bytes into that string? In fact, if we put more than 15 bytes, because when you deal with strings, it's always going to add a null termination, meaning that if we actually put in 16, it would still overwrite one more byte of the thing above it. Well, if we put in more than just the 15 or 16, now it starts overwriting other things because the stack grows down. So the memory control structures are sitting above the data buffer where we're putting our data. So if I put in a bunch of capital A's, and you'll note here that I switched over. I started putting 414141. In case you're unfamiliar with that, that's the hexadecimal value for the ASCII of the capital A. And capital A, or hex 41, is very frequently used in proof of concepts and exploitation development. So you can see now we've put all of these 41s all the way up through here. We've overwritten the saved frame pointer, where the stack pointer was. We've also overwritten the return pointer. That means that as this program continues to execute, when this function exits, it is going to try to execute code at 41414141. The big thing, we have managed to change the instruction pointer, where code will execute from. Now we're going to do more with that soon, but that is at its base the fundamentals of how Stack Overflowing works, and it's enough of the theory for us to be able to do something with it. So we'll turn our attention then to how I find things that are wrong. I could certainly do this with code review and a lot of other ways, but fuzzing is one of the most common ways to do it. Fuzzing means that I'm going to try to put all kinds of input. You could even think of it as random input, though it's frequently programmatically generated, so it's not purely random. There's actually a strategy to it. But it's jamming in random data into every input field, whether that's a network connection, it's a file, it's an input field on a form, any entry, any field that this application has as input. I'll try to put in things that are too big, too small, the wrong type, not put anything in, put in invalid data, whatever I can think of to see if I can break or change the behavior of the application. And that's really my goal. It is simply to get it to change behavior. That's all I'm looking to do. Now, I said that code review could be used for this as well. And certainly, I am a big proponent of code review, but as someone who's doing security research or developing exploits, code review is not something I can always do. If I'm dealing with an open source project, that's possible. If I can get the code, certainly I'll review it. But for most applications where exploitation really matters, we're not talking about open source code. Let's say I'm trying to attack something on Windows, or there's a patch that comes out for something involving Windows. I don't have the source code. So the fuzzing approach turns out to be very, very useful because it does not require the source code. And that's the approach we're going to take in our exploitation. We do not need the source code to be able to attack it. We do need to have a copy of the binary. We do need to be able to run it under a controlled environment so we can observe it running, but that's all we need. The code that we're going to take a look at is a network service. It's going to be running on port 7777, and it's going to accept some input and do something with it. Now, I've chosen to use this particular flaw. I've actually created the code for this because if you've seen demonstrations of this type before, quite frequently they're very contrived. And what I mean by that is it requires that you run this command with this insane command line and feed these crazy arguments to it, which in the real world, if you're already at someone's command line running commands, game's over. You've already won. So that's not really practical. It's not real world. Real world is I've got some remotely executing piece of code that I need to interact with in order to exploit it. And more than that, this piece of code is also multi-threaded. That makes it even more challenging because one of the other things you'll quite frequently see in demonstrations is let's run it under a debugger and watch it run and we can see where the exploit happens and then we can make modifications. And if you're dealing with multi-threaded network applications, that is very difficult to do. But it turns out it's not hard. Let's see what we can do. So we're going to just see our goal, see if we can create some unexpected behavior. That is all we're looking for at this point. So just give me a second. I'm going to turn my camera off to give you a little more screen real estate here. And let me switch over to share over my, my virtual machine and get the slides off the screen here. Okay, we will come back to those later. And let me just show you what we've got here. On this machine, and by the way, if you'd like to try to do some of this yourself, feel free. I've got my email address, I think, at the very end here. Certainly the STI address is there. You can write to us. We'd be happy to send you over the code for this. I think I've got some recordings of this from some different events where we've done it as well. And I'd be happy to share the code with you. The source code for it is here, but we are not going to look at it because in the real world, again, for a commercial application, you would not have the source code. What I'm going to do is simply run the server application. Now, it is a very simple application. With that up and running, I'm going to switch over to my other window here and connect into that service running on port 7777. Now, you likely know that I could use something like Telnet in order to connect to the local host address to my own machine on that port. But I'm not going to use Telnet to do this. The reason I'm not using Telnet is, especially with exploit development, Telnet includes or inserts a lot of extra binary, a lot of extra control codes into the network stream, and I don't want there to be anything else that's going to interfere, especially as I start moving toward creating a proof of concept. because that could end up getting in the way and interfering with what I'm trying to do. Instead, I'm going to make use of another tool that you might be familiar with called Netcat, which is a very, very widely used tool. It's certainly used by attackers, it's used by security people, but it's also used by administrators. It's sort of billed as the network Swiss Army knife. It allows you to create a raw socket connection to anything. It's like using CAT from the Unix world over the network, and that's the idea of the tool. So I'm going to use Netcat to connect to the local machine on that running service. And let me just make this guy a little bit smaller so we can see the other window. This might be maximized. Let me see here. Yeah, there we go. And that way you can see in the background when I connect, in fact, there's connection coming in, so it acknowledges, got a connection in, and it tells me or gives me some prompt. Now, I told you this is a very, very simple service. It's only created for the purposes of the demonstration here. But if you give it some command, it will echo that back. That is the behavior that this system has. So you can connect again, send some other stuff. It will echo back whatever you put in. It's also multi-threaded, so it can handle as many simultaneous connections as it gets. What we know right now is that we have seen a vulnerability announcement, we've seen an alert that says that there is a buffer overflow condition in this thing. Now, hearing that, we immediately know that means too much stuff in too small a space. We would start investigating all of the inputs the application has. In this particular case, our application has only one input. It's right here. So I would start with, let's see, is it one character? No. Maybe it's two characters. Is it no characters? That doesn't do it. Is it 3? Is it 4? Now that's going to get old really fast. I do not want to test this manually. There really are wonderful tools for taking a look at this. One of my favorite is a tool called Sully. Sully is named after the big blue monster from Monsters, Inc. I think there's also a sort of a tongue-in-cheek double entendre because Sully means to dirty something, and that's what we're doing when we're fuzzing something. But it's a fully programmable system, especially good for fuzzing network protocols, where you just want to manipulate certain fields within a network header, for instance. Very powerful tool. But we don't need anything so sophisticated, especially when you're talking about a buffer overflow, too much stuff in too small a space. Let's try this. I'm going to take Perl. Not that you have to use Perl. You can use anything, Ruby, Python, whatever. I'm just using Perl because I always remember how to do the command line here easily. I'm going to tell Perl to print a bunch of capital A's. I'm going to tell it to print, well, let's see, 10. No, let's not go with 10. 100? 1,000? Let's go with 10,000. Let's go with 10,000 A's. Now, I'm just going to run that first to make sure that I've got the format right, because some tools or some languages use the X, others use the asterisk here, so Perl is the X. And I'm just going to pipe that output through Netcat to 127.001 port 7777. And I'm looking for a change in behavior. Now, was there one? Before I answer that, why did I pick 10,000? Well, there's nothing magical about 10,000, but I will tell you this. Programmers are horrible at selecting magic numbers. A magic number is a number that you use in your code for no particular reason. There's no explanation behind it. An example of this would be a programmer needs to accept some input from a user, and they say to themselves, well, let's see, I'm expecting there to be 40 characters of input. How big should I make the buffer? Now, if you're asking the question, how big should I make the buffer, you're probably already doing something wrongly. But let's leave that aside, because this is not a secure programming class. Instead, they say, well, I need 40. Well, they might enter more. You know what's safer? Let me just make a buffer 512 bytes, or 1024. And we tend to use those nice powers of 2. That means that probably not 15, probably not 30, probably not 100, but instead, if you look at 512 or 1024 or 2048, if you look at something bigger than that, that's probably where the overflow will happen. But back to that question about was there a change in behavior, I'm sure that most of you could answer there certainly has, because previously, when we sent input in, it echoed that input back. that didn't do that this time. There was a change in behavior. I would like you to note something else, though. If I connect to that service, it's still running. Again, we've done this, I've written this service specifically for this purpose because this is far more realistic. This is a multi-threaded network service. One of the threads crashed, but the service is still running. Now I want to show you something else that I've done over here. Look at the directory listing that I have here. There's nothing specific you're looking for, but just take a note of what's there, just take a quick look. And I'm going to stop the service and just get another directory listing. And you might notice that there is a new file here that does not appear here. Core. The core dump is a file that can be created. It's not created by default. All Linux machines, all BSD and Solaris machines these days have core dumps turned off. We turn them off because it literally is a dump of the memory of the machine as it was executing. So if there was any private information, any credentials, any passwords, anything like that, it would have been dumped out in plain text. And in fact, if I run strings against core, you can see there's lots of printable strings in here. So we generally turn off core dumps. But core dumps could be quite useful because, as you saw, this application continued to run. So the first indication that someone is exploiting it might be that someone has actually penetrated our system. But what if we were to enable core dumps on our system, at least small, minimalized core dumps? Could I create a watcher that would monitor my system, and if it noticed a core dump getting dropped, it would alert me? Because that would be something unpatched, something that might be even 0-day that's completely unknown, and now I have a way to find it. Again, that's more of a defense, though. Let's come back and look at the core dump. And don't get too excited here. We're not going to spend a great deal of time inside of core dumps and looking at debuggers, but I'm going to open that core dump up in the debugger. When I do, there's a lot of stuff up here, none of which matters. This is all banner stuff. We don't care about that. It tells us this was created by the server. We knew that. There was a segmentation fault. That means you tried to access memory you don't have access to, and here's where that happened. Now, those numbers might look familiar. Those look like capital A's. Let me look at the registers, and in looking at the registers, you can see that the instruction pointer currently has all A's in it, and A's are what I sent. So we have successfully overwritten the instruction pointer. We know that the vulnerability here involves that input field. Let's see what more we can do with it. Now, to be able to actualize this, I'm going to take note of a couple of things. I can see that I'm overriding the instruction pointer. I want to take note, first of all, of the stack pointer as well. Because one of the things I want to check for is to see whether or not the address space is being randomized, which is a defense that we'll talk about at the end. Let me just delete the core dump. I'm going to restart the server, and I'm going to run exactly the same thing again that crashed it the first time. I will look at the core dump again and take another look at the registers. And when I do, I find that the stack pointer is still in the same place. That means that even if address space randomization is turned on, this application does not support it. That makes my life easier, and we're starting with something that's easier. I'll again delete that core dump. I'm going to restart the server, and now I'm going to start doing things with that. The very next thing I need to know is how much space is there from the beginning of that buffer to where that instruction pointer will sit on the stack. The other thing I need is somewhere that I can put some code and then execute it. Now, it turns out there is a memory location that we know and can control. It's the stack pointer. We know that the stack pointer will be here, and I can also put stuff there because the input is going on the stack. So I'm going to just switch over my other window, and I'm going to use Perl for just a second, and I'm going to start building our exploit. Perl-E, I'm going to tell Perl to print. Now, the address is bffed00. However, I started pointing this out before and didn't get into it much. However, the computers we use today are little endian machines. You and I are big endian things. If I ask you to write the number 1024, you would most likely start by writing the number 1, then you'd write the 0, then the 2, then the 4. You start at the biggest end of the number. Your computer, Intel-based computers, AMD-based computers, in their memory, store the littlest end first. That means that we'll store it a byte at a time. We put the 00 first, then the ED, then the FF, and then the BF. So we're just reversing that address. That's the little endian notation. That is the last hard thing, by the way. So if that doesn't make a lot of sense to you, that's just how we do it. We have to reverse the number. I'm going to store that into a file that I'll call return, so I don't forget about it. The next thing I need is to figure out the space between the buffer and where we are in the instruction pointer. Now I could bring it into a debugger and count bytes, and that is way too hard. Instead, I could just use some tools. Now normally, I would actually use a tool that's part of Metasploit. The Metasploit framework, if you haven't heard of it, is a very well-known exploitation tool that allows you to lay different exploits together. But it also is used for exploitation and development and has a set of tools in it for doing exactly what we're about to do. However, it's become a little bit finicky to get installed, and in particular on my machine here, on this VM, it just won't cooperate. So I'm not going to try to get that running. Instead, I went out and found a different one that works exactly the same way. It has a tool called Pattern Create. It allows me to create a set of characters. So if I tell it to create a set of characters that's 2,000 bytes long, it creates a pattern for me. And what I'll do is take that pattern and push it through Netcat on port 7777. This process will crash. We get a new core dump. If I look at the core dump, you'll see that the address here has changed. It's showing me where it tried to run code. Now 41, that's the capital A. It turns out that all of these are printable characters, and it's representing characters out of this string. And what I can do with that, let me just pull up the help for this. What I can do with that is I can extract exactly where that is. So I simply tell it how long that string was, and then I tell it what the value was that we crashed at. So it's the same value we had from the core dump. And it comes back and says, oh, that's 132. That's it. No stepping through debuggers, no counting bytes in memory. That's way too hard. So people who are showing that in demonstrations, they're just trying to make this look hard. Let me restart that server. And I'm now going to create another file here. Now, I'm just going to use X's to use something different. And I want to print 132 X's. Let's make sure that's right. That is right. And then I'm going to push that into a file I'll call padding. At this point, I've got the padding that takes me up to where the return pointer will go. Then I've got the return pointer, where the stack pointer is. Now I just need some shellcode. Now, we're not going to write shellcode. Instead, I've got some. In these days, there really is no need to write shellcode unless you're trying to do something really special, because there are repositories full of shellcode. So we're going to go the easy way here. I'm going to just compile this. I'll use GCC, and by using the -C, I'm telling don't try to make it an executable. Just compile it to object code, so I get that .o code back. At which point I can use object dump to show me what that looks like. So on the right-hand side, it shows me the shell code, the assembly code I had. And on the left-hand side, it's showing me the actual raw bytes that gets translated into. I need to get those bytes into a file. I could either do that by hand, which is a pain in the neck, or I've got a little script here that just runs object dump or obj copy, because I can never remember the right command line for this. So I'll just run obj to bytes against that file, and it creates a file for me called shellcode.o.bin, and I want you to notice the size of that, just 28 bytes. Now I actually have spent some time, I've done this with with some of the largest microcontroller manufacturers in the world, PLC manufacturers, and other organizations too. I've done secure C and C++ coding training for some really big organizations. And when I interface with the programmers and start talking about these issues and how to write defensible code and writing secure code in C, C++, C#, one of the objections they have is, yeah, okay, we've got an issue, sure, but I mean, what can you do with, say, 132 bytes, which was the size of the buffer we had? That's the wrong question, because in this case, I want you to note the size of the shellcode. It's only 28 bytes. I didn't even need the whole 132. And in fact, I could use more than the 28. I'm not limited to the size of the buffer. I'm limited to the size of the stack, especially in this particular case. So exploits can be quite small, and this is fully working shellcode. Programmers, when they see the size of that, they're usually thinking about creating a very simple program like Hello World. And when you compile that, the smallest version of it is going to be about 12 kilobytes. That's because it has object headers on it and there's linkage information and library data and everything else. We don't need any of that. This code is getting injected into an existing running program. At this point, though, we are ready to put these pieces together. So what I'm going to do is I'm going to send or print the padding. So that fills the buffer, followed by the return pointer, followed by the shellcode. And I'm going to send all of that into this service and see what happens. Now I'm going to warn you, this likely won't work the first time, but don't worry, we're close. Well, it connected, but then it failed. Why did it fail? I'm going to get to the answer very quickly, but the answer of why it failed is a little bit technical. If I take a look at the core dump, I can see that it's crashed, and it's crashed in an unfamiliar area. Where is that? Don't worry so much about where that is. Instead, we'll take a look at the registers. I see the registers. Yeah, we're in the same area. It looks like the stack pointer's okay. I've got the 585858. That's the capital X's that we used. Something went wrong. Here's what I'm going to do. I'm going to print out 128 bytes of memory, starting out at 0xBFFF. Let me use EC00. EC00. Oof, that already looks bad, I know. Hang on one second. We're going to compare this to something. I'm going to dump out the shellcode.o.bin, and I just want to take note with you of the first few bytes of this. In fact, it's probably better for me to do it this way. So we've got B8322F73. Now, if I look inside of this, inside of this mess that looks really unpleasant, it turns out that the thing I'm looking for, it is in here, but it's not at the address I thought it was. It turns out that it's offset just a little bit. And I've already forgotten the address that we were supposed to be at. But I see over here, oh, B8322F73, that looks familiar. 2F73, B832. All right, so it looks like we're over here. That's where I should have been, and I missed it because I think I was at ED00 or something. I can't remember. It turns out that it's 4 bytes off. It's just 4 bytes off. Now, I'm going to exit out of this because we're headed toward a really complicated technical thing, and I'm just going to fix it. And as I fix it, I'll tell you why it happened. All I'm going to do is come back here to where I created the return address, if I can find it. There we go. And I'm going to change that from ED00 to EZ04. And that really ought to do it for me. And I'm going to send that same thing against it. And okay, I'm still off a little bit. I'm not going to fight with it too much. What's happening is that my code is misaligned a little bit. And the reason that it's misaligned is because it has to do with how we store things within the memory. And actually, I'm looking here. So ED, E0, I think I'm a little bit further than that. 1, 2, 3, 4, 5, 6, 7, 8. Looks like I'm 8 bytes off. Let me just try that one more time just for kicks here. Let me fix that. Maybe it was 8 instead of 4. Oh, nope, still off. Just one more try, and then we're going to give up. Ah, there we go. So, all right, it had to do with byte alignments in the stack. This is a very technical thing, but within the stack, because of the machine architecture, it's going to align the stack to certain boundaries. So my data just ended up in a slightly different place than I expected it to. But as you can see here, with a little bit of knowledge, I was able to find it in just 3 guesses. How do I know I found it? Well, you'll see that over here, I'm still sitting at this prompt here, but in the back end, notice that we now have a prompt. And we're now able to run commands over here. Now, to be fair, we've managed to create an exploit that runs a shell on the remote machine. So I fully recognize that getting the shell running on the remote machine is not terribly impressive, but this is just a proof of concept. Could I use a different piece of shell code that gives me remote access to that shell? Sure. Could I use a different piece of shell code that creates an account for myself or creates a network listener or does anything I want it to? Yes. My goal was simply the proof of concept. We've successfully achieved that. We've got the proof of concept. So once we're at the proof of concept, we can then expand that to make it do anything that we want. What can I do from here? At this point, the application that we've looked at, let me delete that core. The application that we've looked at, this has no protections in it. This is just a raw binary. It's got no ASLR in it. It's got nothing else going on. How could I make it better? Let's talk about making it better. And by the way, we were able to get to the working proof of concept. So it's 2:51. I think we had about 5 minutes of intro and lots of discussion of theory. So really, if you took all that out, you're probably talking about 5 or 10 minutes to get a working proof of concept here. Let's make it more difficult. Let's make it a non-executable stack. Now in this case, I've just recompiled it differently because making something a non-executable stack, while it can be done in hardware, it is rarely done simply in hardware because so many of our applications can't support it. One of the reasons is that programmers do crazy things within their code. So non-executable stacks or data execution prevention is not something you can always enforce. This piece of code simply has the non-executable stack bit flipped. I'm going to try to send that same code, that same exploit at it, and we see that something happened, and this was my working code. It didn't stop. Let's take a look at the core dump it creates. You'll notice that this address should look familiar. That's the address in the stack. Now the non-executable stack says you can't run code from there, from the stack. We fixed the problem, right? Can't be compromised. Well, that was the idea behind creating the non-executable stack, but it turns out that simply marking the stack non-executable does not make you safe. Let me show you why. And after this one, I think I'm going to go back to the slides and just summarize because we're really running short on time. But if you're interested in more of this, you can write to me. I'm happy to talk about it. And again, I can point you at some videos where we've got the whole demonstration all the way through the end. So I'm going to open up that server NX, and I'm going to use info functions. And it shows me all of the functions that are in this application. In this application, you'll note that most of them have 2 copies. Here is set sock opt, and then there's set sock opt at PLT, procedure linkage table. So these are all library functions. And for each one of them, it gives me a memory address on the left-hand side. Further down, just to make our life easy, there is another one here. Let me find it now. Let's see. Oh, here we go. You'll find that some of these, debugger, vulnerable, sigchild handler, get IN address, main, there aren't doubles. These functions are actually implemented within that piece of code. And in this case, we've got an address of 080488F1. Watch what we're going to do. I'm going to change the return address. I'm doing nothing else. I'm simply going to change the return address to, and I'm going to write it backwards, F188 0408. That's all I'm going to do. And then I'm not going to send the shellcode. I'm just sending that. And, well, I didn't get anything back here. Let's see. Did I get a core dump? I don't recall if I deleted the other core dump. I did get a core dump. I'd have to fight with this a little bit more. What's it telling me here? Yeah, something went a little bit wrong there. But notice that I'm no longer crashing in the stack. What happens is, I do want to just, I feel like I want to just check that address. Let me just scroll back, see if I copied that correctly. So 080488F1, yeah, that looks right. I'm not going to fight with it. The point is that it turns out I don't need to run code from the stack. That's just really convenient. And in fact, that's a lesson for how it works in terms of defenses and exploitation. If I'm able to create that unexpected behavior, and then we were to introduce something like a non-executable stack as a way to defend against running on the stack, no problem. If there's a function that does something I want, even though I don't have the rights to get to it, by simply providing that address as a return address, I can cause the function to now return to that code and execute it. Arc injection is what that's called. Or I could return to something in the procedure linkage table, which is called a return to libc. So I could potentially build the stack space, build all of the arguments that I need on the stack in order to make a call to, say, the system function or any other function I want to, and execute that code. Going a step beyond is something called return-oriented programming, which is very, very similar to what we've just described, with one adjustment. If I simply return into the library or return into an arc injection, that's running existing code, which, by the way, is still executable because it's in a code segment. It is return-oriented, but return-oriented programming goes a step further. It uses the idea that could it be that there are pieces of code, small pieces like Lego blocks, sprinkled throughout your executable code space, that if I were to assemble them in the correct order, I could execute any arbitrary code I want to. So by simply chaining together many returns to the correct addresses, I can execute any arbitrary code I'd like. That's the goal of return-oriented programming, which is technically more challenging, but it's really not hard. What if we randomize the address space, which is the next main defense against this? Well, again, it still turns out that even with a randomized space, it's the data that's going to be randomized and not the code. So the arc injection, the return-oriented programming, the return to libc all still work. But worse than that, simply having ASLR on doesn't mean that our system is defended, because many of our pieces of code will not support it, which is why even in something like Windows, while you could have hardware-based DEP, you often can't turn it on. Because if you do, there are programs that you rely on that simply will not function because they were not compiled as position-independent code. They rely on the ability or on the data being in the same place every time. There is another side effect of this return-oriented programming in the arc injection. It's code signing, which is another approach we take toward making sure that bad things can't happen. But it turns out that if I'm using return-oriented programming or an arc injection or return to libc, I'm not adding code. I'm using your signed code to do the bad thing. One of the very best protections, though, is this thing called a stack canary. This is very difficult to beat, or can be very difficult to beat. It's only difficult if there aren't a set of circumstances that allow me to write to arbitrary memory locations. As long as that condition exists, this is not hard to beat at all. But without that condition, there's no direct way to go against the stack canary, which is just putting a little bit on the stack between the data and the return pointer. And if that becomes corrupted, it's like a canary in the coal mine. It allows us to detect that that's happened and then react. In other words, the program would crash, knowing that the canary has changed. But stand back for just a moment. I know there was some technical stuff in here, and there was probably more debugger output than you wanted to see. But standing back from a high level, how hard was that really? I'm not asking if you could go do that tomorrow. I'm asking, do you think that there are just a handful of people in the world who can do this? Or is it a matter of just taking a person with a little bit of knowledge, maybe even just some internet research, and they could go about doing the same thing? And what does that say to you about your mean time to repair? Remember, in surveying what's going on in organizations, even when we say 30 days, we're nowhere near that. And if you look at the news today, Honda today had to shut down a factory because it turns out that they just found WannaCry running around in their network. Now, how many of us reacted to WannaCry? That was a big deal. But here they are, more than 30 days later, just realizing that this is floating around, and they're still not fixed. So, do you think Honda is alone, or is the problem bigger than that? Exploitation really is not as difficult as people tend to think. At this point, I'm really done with the majority of the presentation. If you folks do have questions for me, you're more than welcome to ask. And this is, much of what's taught here is actually part of some of the classes that we've got within the Masters of Information Security Engineering program at STI. And there are also some graduate certificates that are available as well, particularly with regard to penetration testing, that get into some of the topics that are here. So if you have questions for me about the content, or if you have questions about the college, you're welcome to ask those, and I'm sure Eric could handle this. If you have no questions, I do appreciate you coming. Feel free to write to me if you'd like to. I don't have my email address up here at the moment. Oh, and I can't add it to this because it's a picture. If you write to info@sans.edu, they'll be sure to get that into my hands.
All right, David Hoelzer, thank you for the presentation, and I'd like to thank everyone in attendance. This concludes our webinar, and you can tune in for our next webinar at cyberstudents.org.